head of the department. On behalf of Department of Chemistry, we would like to express our gratitude to Professor Hyun Sohn, PhD, who is this morning will deliver guest lecture, we call it, entitled CO2 free hydrogen transportation technology, ammonia synthesis and decomposition. He is from Korean Institute of Science and Technology, Center of Hydrogen and Fuel Cell Research. And I wish you all have a wonderful time, fruitful lecture from experience, knowledge, expertise from Professor Hyun, and have a good lecture. Thank you.
Nice to meet you all. My name is Sohn. I'm actually a senior researcher in Korean Institute of Science and Technology. We are a government research center located in Seoul, the capital. Thank you very much for inviting me. Actually, this is my first time coming to Indonesia. And then I came around 9 p.m. yesterday. There was pouring, a lot of rain was coming in, a lot of thunder. And then I took a taxi and I was kind of scared, but it seems the taxi driver was very calm. He was like, we'll get there, don't worry. But finally, yeah, I came to hotel and today I'm very happy to be here. So today I'm going to talk about the basically hydrogen, but more related to hydrogen transportation. Right now, South Korea and Japan are changing its strategy to import hydrogen for overseas and then use it as an energy source. I work on catalysis. I'm a heterogeneous catalysis person. I work on metal, metal supported on metal oxides catalysts. But today, because if you talk about too much about the research kind of going, so today the talk will be more general of how ammonia is right now used as hydrogen transportation technology, and how much world is actually focusing on it. So let's begin. So usually when I start my presentation, I bring this map. If you see this map, you can see these yellow stuff, right? Those are the oil reserves. And so if you look at it, there's a lot of, in United States, in Russia, Middle East, and also in Israel. If you look at, for example, Korea and Japan, you can see there's not much oil, right? So in our case, what we do is we transport these oils, because it's our energy, right? To overseas using the ship and then bring it to Korea and then import the energy. When we import these oils, right, we use it from making ethylene to synthetic plastic, right? And then we use these oils vehicles and then of course to generate power for the electricity. Right? Those are the energy sources that we get imported from overseas because we don't have much. Now, this is right now the current energy system in the world, right? Oil, natural gas, and then transportation. This will change in 2050. Let's look at the map. It will change like this. Now, you can see still in the United States, and China, and also Middle East has a lot of energy still, right? A lot of energies. And also Southeast Asia also has a lot of energies. Especially the new emerging country is what? Here, Chile. Chile has a lot of energy sources. But if you still look at it, South Korea and Japan has zero energy. So still, what we have to do is we have to import these energy, mostly renewable energies, solar energy, to our country. How do you do that? If you have an electrical grid, that would be awesome, right? Because everything is connected and we can just take the energy. But it's not possible. So we still have to import this energy to South Korea, and that can be done with hydrogen, because hydrogen can store energy, and hydrogen is an energy carrier. So once we have those energy, bring it into South Korea, we can put it into a fuel cell, generate electricity, right? Or you can also combust hydrogen to get heat and then eventually electricity. So this is why we have to import hydrogen. And so even in South Korea, people say that why do we have to import hydrogen? We can make it our own self. We can use it using hydro electrolysis, water electrolysis, right? You can produce hydrogen. But a lot of people say that in Korea as well. But if you look at the price of hydrogen that is produced, this is ROK, Republic of Korea. Using solar panel in Republic of Korea, South Korea, this is the price of the hydrogen cost. But if you look at the other countries, for example, like China or Chile, and also there's also Indonesia solar power right here. It's almost half of what we produce. So this is using renewable energy electrolysis, producing hydrogen, and it's even cheaper, of course, if you use fossil fuel. Right? If you use natural gas, you can produce hydrogen even cheaper. But still, it's almost twice expensive. So from our perspective, if including the transportation cost, if the hydrogen import cost is much cheaper than what we generate, we definitely have to import hydrogen. So this is the first reason why right now South Korea and Japan is trying to import it, because it's so expensive to produce in our country. Okay. So now I kind of talk about why we have to import hydrogen, but how are we going to import hydrogen? Hydrogen is a gas, right? So in order to put it into a big carrier and then transfer it to Korea, that gaseous hydrogen should be stored in some different way. And that storage technology has also to be CO2 free, carbon dioxide. There's a lot of ways to storage hydrogen. There's actually a lot, but usually we say there's only one. The first one is physical, as you know, compressed hydrogen. So you try to compress it in a very high pressure, 700 bar. Then you can store more hydrogen in a container. Second one is liquefied, right? If you liquefy minus 253 degrees, it becomes a liquid, and then you can transport it because it takes less volume, right? And those are physical methods, and then the other one is material. One is react hydrogen with metals, and then you store it in metals. And then another one is organic hydride, react with hydrogen with organic. The third one is react hydrogen with inorganic hydrides. These are all liquid. This is solid, and this is liquid. So you can store more hydrogen in a same. Now, when you compare these five, so let's say if I want to bring hydrogen, for example, like from Indonesia, to bring hydrogen to South Korea, there you can consider 5 ways, right? But if you want to consider 5 ways, there are 2 concepts you have to first consider. The first one is gravimetric hydrogen storage density. It means if you have let's say if you have a 10 kilogram container, and then if you can store 1 kilogram of hydrogen, then the gravimetric hydrogen storage capacity is actually 9 kilogram, right? So total is 10 kilogram, and then if you store 1 kilogram hydrogen, that's only 10%. Sorry, that's different. So this is how much you can store hydrogen in terms of based on the weight of your container. And then another one is volumetric. It means how much hydrogen, kilograms of hydrogen you can store in a cubic meter. Now, if you want to transport hydrogen, this is much more important. Because why? Because you have a limited space that you can store in a carrier and ship. So this is very important. And if we can compare all those finds, let's say first let's talk about compressed hydrogen. So if you look at here, this is the gravimetric density, y-axis is the volumetric density. The gravimetric hydrogen density for pressurized hydrogen is very low, which means it's very, very heavy, right? So if the container is, it's almost like 1%. So it means if the container is 100 kilogram, and then if you can only store 1 kilogram of compressed hydrogen, which means very heavy, which means you cannot put it into a ship. So usually compressed hydrogen is not considered for overseas transportation. The second one is liquid hydrogen. which is over here. And usually liquid hydrogen is around 10%, which is okay. But if you look at the y-axis, this is the volumetric hydrogen density. Pressurized hydrogen is also bigger. Liquid hydrogen is about like 1.5 times higher. Okay, so this is compressed liquid. Let's look at organics. Organic. So one is methyl cyclohexane. So if you imagine a toluene molecule, you can store hydrogen. You can react with hydrogen. That toluene becomes methyl cyclohexane, and then you ship methyl cyclohexane to the designated place, and then if you dehydrogenate, you get a toluene, and then you ship it back. So that's how you actually transport hydrogen. But if you look at that, that's also volumetric hydrogen density is around even lower than the liquid hydrogen. And then it's also quite not heavy, but moderate. And then the fourth one is metals, where you can store hydrogen metals. These are all types of metals that you can use, but the red ones are not reversible, which means if you store hydrogen into metal, you cannot take it out, or it requires very high temperature. So it's not very practical to transport hydrogen. Usually, these are the common ones that are used. These are based ones, but you can see also because it's metals, it's very heavy. But also volumetric hydrogen density is pretty similar to methyl cyclohexane, liquid hydrogen, and a little bit higher than the compressed. You know, these metal hydrogens are used usually because it's very submarines. Because submarine has to submerge, right? So usually metal hydrides are placed in a submarine, and then with a fuel cell, and then you can that hydrogen can operate the submarine, and because it's heavy, it's good for submarine application. Now, the last one that I'm going to talk about today is ammonia. You can see it's all the way here, right? The gravimetric hydrogen density is almost 17.8%, and the volumetric hydrogen density is very high. So this is why ammonia is right now considered as a very good candidate for hydrogen storage energy transportation. Some of you may wonder why ammonia is a hydrogen carrier, but if you look at the structure, right, NH3, you can think of that hydrogen is binded to nitrogen. So this is the hydrogenation step, which is the ammonia synthesis. So hydrogen is binded to nitrogen. So in one place, for example, in Indonesia, you make ammonia. You basically do electrolysis, get hydrogen, bind it to nitrogen, make ammonia, and you ship it to South Korea. Once you ship it to South Korea, you decompose. You get hydrogen, and hydrogen we use, but the nitrogen, because in air everything 80% is nitrogen, so you just expose to it. So this is how hydrogen is transported using ammonia as hydrogen. You can see it's a one way. It's not a both ways. It's one way. In one place you make ammonia, in another place you decompose to supply hydrogen. The reason again why ammonia is so a very good candidate is because of this. It has very high gravimetric and volumetric density. So in other words, basically you can load more hydrogen in one ship. That's why. And then ammonia is already used in worldwide a lot. So the safety and also the infrastructure is very well established. So it's a very good candidate. And because of this is our South Korea's hydrogen economy plan, basically. So what we are going to do is we are saying in 2030, in our country, to produce electricity or to use any energy using fuel cells or other applications, we have to have 3.9 million tons of hydrogen that we require in South Korea. But if you look at it, 1.96 million tons will be imported from overseas, and then that will be done with ammonia. Okay, this is not just our country's strategy; it's also from Japan and United States and all over the world. Right now, ammonia is the first candidate to really transport hydrogen among the countries. And so, This is a report that was generated from the I forgot the name, but it's the World Energy Institution, and you can see these blue lines are the ammonia flow. And so in 2050, right now, as we transport natural gas, oil, in 2050, those will be replaced by ammonia. That's what they're planning, and then you can see that these blue lines are all ammonia. But if you look at Europe and North America, you can see that most of them are green. Green are it means that hydrogen flow within the region. So what that means is Europe and North America does not have to import hydrogen. They can produce hydrogen within their country, and then they can just use it within their country. So in these cases in Europe, right now, the most best candidate for hydrogen transportation is hydrogen pipelines. So right now in Europe area, they are installing hydrogen pipelines, almost investing $1 billion right now, and rather than using ammonia as a chemical. But if you look at here, Republic of Korea, South Korea, and Japan, they're all going to use ammonia, and also Southeast Asia and Australia. There will be a lot of ammonia imports and transportation. If you look at here, there's a small one which is called LHC. LHC is the organic hydrogen storage technology, and then the gray one is liquid hydrogen. The problem of liquid hydrogen is you have to constantly stabilize the temperature of minus 253 degrees while you're importing, which requires a lot of energy. So, and also there's not a big ship right now that can handle that kind of amount of liquid hydrogen. So the application is right now not very practical, and also because if you want to travel a long distance, it's not really practical. So liquid hydrogen and the LHC is only for short distance, but majority. Okay. So far I talked about ammonia, like why we have to use ammonia, why we have to transport hydrogen. So right now I'm gonna start from ammonia synthesis and then all the way to the ammonia decomposition. So I already gave you an answer. There was 3 Nobel Prize related to ammonia synthesis. 3 Nobel Prize. These are the Nobel Prize winners, 3 of them. This is Fritz Haber. This is Carl Bosch. So this Fritz Haber. So right now, the chemical equilibrium. Right now, it's so when you have a lot of, if you look at the chemical equation and the number of moles is higher on the product side, if you increase the pressure, what happens? It goes to the reactant side, right? Your conversion level goes down. Right now, it's in textbook, right? So we all know. But in that time, they didn't know that. So what they found is because if you look at the ammonia synthesis reaction equation, if you increase the pressure, right, you get more hydrogen, right? Because it's 4 goes to 2. So this is what they found out. Fritz Haber and Carl Bosch, basically they're German chemists. They're I think German chemists, and Carl Bosch is from Pass. This is the biggest chemical company in Germany. And then Fritz Haber was a professor, and then they did a technology transfer. And then they eventually produced mass amount of ammonia in 1930. This high pressure, high temperature reactor. And they got a Nobel Prize, both of them. The third person is Gerhard, and he got a Nobel Prize because of he revealed the catalytic chain. So iron catalyst is used for ammonia synthesis, and then he revealed a very detailed mechanism. 3 Nobel Prize was ammonia is the major reason why there was so much increase in population in modern history. Because of the mass production of ammonia, a lot of crops were generated more, and then there's a boom in population. That's a lot of people's science, a lot of science. So because of this, the ammonia synthesis process right now is called Haber-Bosch. So Haber-Bosch process. So ammonia synthesis process is Haber-Bosch. Haber-Bosch process is basically this. What it does is you first feed natural gas and air. So the reason you free natural gas you need hydrogen is basically hydrogen is from methane, also water. So you're doing a steam water, and then air you need nitrogen. Nitrogen, so that's the nitrogen force. So when you do a steam reforming, what you get is hydrogen, nitrogen, and carbon monoxide. And then you do a fuel shift using water. Basically, you do this is to get more hydrogen. And eventually you get nitrogen, CO2. You remove CO2 and then you do a synthesis with nitrogen, hydrogen at very high pressure and very high temperature. This is how you get ammonia. But if you look at the whole process, as you can see, carbon dioxide is coming out, right? Where is it coming from? It's coming from natural gas. So if you get the hydrogen source to synthesize ammonia from a natural gas, that is not a renewable, the whole process is a lot of carbon dioxide emission process. So if ammonia wants to be truly used as a hydrogen transportation technology, the hydrogen source has to come from water, from the water electron. That's actually first biggest problem, but which is also resolvable. Okay, so once ammonia is produced, this is the worldwide ammonia distribution. You can see almost 220 million tons of ammonia is shipped in all over the country. Around 20 million tons are traded internationally. We're at 20 million. And then look at here, carbon dioxide emission from ammonia synthesis at 420 million tons per year. That's almost 10% of total carbon dioxide emission. So from ammonia synthesis, there's a lot of carbon dioxide produced, and ammonia is also almost top 5 synthesis chemical in worldwide. Do you know what's the first one? What's the first chemical that's produced worldwide? It's ethylene. Ethylene is number 1. Plastics. So ammonia is also very a lot produced. Where this is the global ammonia production. I'm sorry that some is Korean. But so this is the capacity where the ammonia synthesis plants are located. Mostly is in China and also United States. And then, but China and United States, they synthesize ammonia, but they use most of them within their country. So what's the this is the export. Who exports ammonia the most? So number 1 is Saudi Arabia, Russia, and then Trinidad, and then the green one is Indonesia. So Indonesia is the 4th largest ammonia export country. And then South Korea is the 4th country in world. So right now we import a lot of ammonia from Indonesia as well. So this is how it's actually transported right now in worldwide. They got a picture from a satellite, okay? And then they did some statistics analysis, and then they found out these are the places where ammonia is mostly used. Let's look at this picture. You can see a lot of use are in the middle of the United States, some in Africa, a lot of India, and then also in the middle of China. So where it is used? It is used for, like I said. So in the United States, this is just ammonia, pure ammonia. They just spread it on the ground. And what it does is ammonia gets into the moisture in the soil, generates ammonia ion, and these shows multiple reactions, and then eventually NO3 minus, which helps to grow crops very well. And so this is how ammonia is mostly used right now. And then these are United States, middle of United States. You can see these are all ammonia facilities, and they also have these long pipelines of ammonia in the United States. So this is they are very familiar with ammonia, and then a lot of them is. Okay, so these are just a few South Korean companies that import. But what I want to really show is this. So we are importing. This is how much ammonia we are price per ton. So if you look at it, it's around 353, right? 300, right? But it suddenly increased, right, to 500. And then it increased to 800,000. Well, why do you think it increased? Ammonia price, worldwide ammonia price. Yeah, because ammonia is what used made from natural gas, right? And because of the war, Ukraine war, the natural gas price sharply, significantly, and also affected ammonia price as well. So ammonia is very expensive. And the problem is now, if it's this expensive, we cannot use it as a hydrogen carrier. So it's very important to have ammonia price very close to $300 per ton, which is made from natural gas. What I'm saying is the ammonia that are generated from water electrolysis, the price has to be similar to what we produce now. Yeah, it has to be very similar to use as a hydrogen transportation carrier. Okay, so again, a lot of carbon dioxide is produced because ammonia is getting from natural gas. So to really use ammonia as a CO2 free hydrogen carrier, it has the ammonia, the hydrogen. The hydrogen should come from water electrolysis using renewable energy. That's the key. Okay, so you may wonder, so then it's really a lot of green ammonia. So ammonia is synthesizing from that electrolysis. So the ammonia that are synthesized from natural gas is called gray ammonia. The ammonia that are synthesized from water electrolysis, renewable energy, is called green ammonia. And the green ammonia plants are right now constructed all over the place. The first one, the biggest one, is in Saudi Arabia, which they said that they're gonna build it. Investment of $5.9 billion. That's quite a lot of money, and then they're trying to build a green ammonia plant. And then if you look at the picture here again, using the renewable energy, then what electrolysis, get hydrogen. You also want to separate nitrogen from air, which also can be done using renewable energy. So nitrogen and hydrogen, and then you produce ammonia, and then you ship it to, for example, South Korea, and then you decompose, and then you can use it. So this, what they said is the annual production is 1.2 million tons. And this much of ammonia, if you want to produce that much ammonia, you need a 4 gigawatts renewable energy. That's quite a lot. So they're trying to build in Saudi Arabia. The second biggest one is the Asian renewable project, which is proceed in Australia right now. This is even bigger. They are using 25 gigawatts, and they're trying to produce 9 million tons of ammonia. If you look at the map, this is the Australian map, and there's a small region where they're going to put a lot of solar panels, and then wind renewable energy to produce ammonia. This is almost investment is $22 billion. $22 billion. And then recently, BP is a UK oil company. They say they're going to buy 40% of this 30 billion. It's very serious, and they said they're going to buy it. But I brought the article here, and then if you read it through, eventually what they say is they are buying it to enabling South Korea and Japan to decarbonize. So that means they're doing this because they want to sell ammonia to us in South Korea and Japan. Now, right now, another problem of ammonia hydrogen transportation is there's not much buyers, right? Because if you make this much of a green ammonia, someone has to buy it, right? But the only buyers is South Korea and Japan at this point. So that's also another problem. They're making these green ammonia plants are generated all over the world, not just Australia or Saudi Arabia, the United States, Middle East, Europe, Africa. But the problem is there's no buyers at this. So that's also another problem. So the demand is very small. And then there's some more. This is from South Africa. They're also trying to build 780,000 tons of ammonia plant. And then another big company, big country is investing a lot of ammonia is the United Arab Emirates. They are also building a lot of green ammonia plants, but they're focusing on is so green ammonia is from natural gas, green ammonia is from water electrolysis, right? In the middle there is blue ammonia. So what's blue ammonia is you make ammonia from natural gas, but you capture CO2 and then or just implement it in underground. So if you remove carbon dioxide, you call it blue ammonia. There's gray, blue, green ammonia. They are focusing on blue ammonia. They already have exported blue ammonia to Germany already. A lot amount of ammonia was actually exported to Germany. So this is also a big company that is currently going on. This ammonia strategy was actually first introduced from Japan. Because Japan actually had worked on hydrogen economy more than 30 years ago, because they knew that there was not much energy they can use. So eventually they have to import energy using hydrogen. So they also went to Saudi Arabia and the UAE and then do MOU and then say, get contract that we're gonna import ammonia. After Japan, we also in South Korea, we also went to Arab Emirates and then Saudi Arabia to do some contract and to get import ammonia. So this is all the things that is going on right now in worldwide. Ammonia is definitely going to be, I think, used as a hydrogen transportation technology at this moment, which is the first candidate, because like I said, ammonia, it's already traded a lot, and then it has the most highest volumetric and gravimetric hydrogen density. So definitely the corporations will use ammonia to import energy at this point. Okay, so what ammonia is synthesis, right? So so far I talked about ammonia synthesis and how much is synthesized, who's exporter, and then green, blue, gray ammonia. So let's say if we import, or from our perspective, if we import ammonia, actually we have to decompose. So in our country, South Korea, research is more focused on rather than ammonia synthesis. A lot of research funding is focused on ammonia decomposition. So if you look at ammonia decomposition, the reaction is there's 2 moles of one nitrogen and three moles of hydrogen. It's unfortunately this is endothermic reaction. So it requires energy, which means it requires heat, and also it requires catalyst. But if you look at this, if you increase the pressure, right? This time ammonia synthesis, you get more conversion, but because this is the opposite, if you increase the pressure, you get less hydrogen from the reaction. So conversion goes down. And then usually ammonia is imported in liquid, so you have to first gasify. So that also requires energy. So when you get ammonia, so again, when you import ammonia as liquid, there is an energy required to gasify it, and then there's another energy required to which is kind of how to say a rate determining step of why ammonia is not used as much as because it goes as well. Okay, so once we get ammonia, of course, there should be ammonia storage tanks in South Korea. I will give an example for South Korea. We need ammonia storage tank. We also have ammonia storage tank right now because we are already importing ammonia. But again, you have to vaporize ammonia, put it to gas, and then you have to decompose. So once you decompose ammonia, what do you get? Hydrogen, nitrogen. And then there's always unreacted ammonia, which is around 2,000, 3,000 ppm of unreacted ammonia. So you need to remove unreacted ammonia first, right? You need to remove that, and then what you get a mixture of hydrogen and nitrogen. If you get a mixture of hydrogen and nitrogen, you can directly connect it to a fuel cell and generate electricity. You can also separate nitrogen and hydrogen, make high purity hydrogen, and then you can fuel it to a hydrogen car. At this point, South Korea also has a lot of hydrogen cars, but these days I think battery cars are more competitive right now. I want to say that in terms of small size vehicles, batteries are sometimes has more of the advantage. But when you think it's because the battery the amount of that needed for that car, that battery size is okay with that single car. But if that car becomes a truck and a train and an airplane, batteries cannot be used for that. In that case, there's no way you can. There's only one way is using a fuel cell. So a lot of trucks and trains are now developed also for airplanes. I think I forgot the name of the company, but European company, they also have build airplane, liquid hydrogen based airplane with fuel cells that can handle 20%. That's already practically running at this point. So you have to know that these are getting very, very fast. And it has to be done with the fuel cell. It cannot be done with that. Okay, so I'm from KIST, and this is the first demonstration project. So what it means is this is the first small scale where you decompose ammonia and then you can generate electricity. This is what we made, and this is the reactor basically, and this reactor is filled with this catalyst. If anyone works on catalyst, usually in universities they powders, right? But because this is like a practical scale, we use a beads catalyst. This was filled in the reactor. So ammonia gets in, right? And then ammonia is decomposed again, hydrogen, nitrogen, and then unreacted ammonia. There is a zeolite column behind. That zeolite column absorbs unreacted ammonia, and then the hydrogen and nitrogen is fed directly to a fuel cell. And then it can generate electricity. And then we were able to fly a drone with that electricity. We generated 1 kilowatt. Unfortunately, it's not wireless. It was with the line, but able to demonstrate. This was the first demonstration project that was done in South Korea from Ammonia. And then after this, it was pretty good. So Hyundai Motors came to us, and then they funded us. And then we increased 5 times larger. So this is for 5 kilowatts now. So basically the system is pretty much the same. So ammonia decomposition, unreacted ammonia removal, and then it directly fed into water. So this is the second one. And then after this, government say, okay, we're going to use ammonia definitely. So we build a bigger one. Basically, the concept is the same. So ammonia gets in, it is decomposed, unreacted ammonia is removed, and then this time hydrogen and nitrogen is separated. Okay? And then this nitrogen has a purity of 99.97%. Now this system can generate 1.8 kilograms of hydrogen per hour. Do you have any idea how much that is? So one Hyundai motor hydrogen car takes 5 kilograms of hydrogen, which can drive around 400 kilometers. So this is not that big, right? You have to run this process for around 3 hours, then you can put it into one car. So it's not that big, but still it's kind of big. But so this much of the hydrogen was generated, and then with 99.97, this project was done in 2021. So 2 years ago it was finished. So let me show you kind of details. So this is the reactor. Okay, this is the reactor. This is the ammonia, unreacted ammonia removal section. This is the nitrogen and hydrogen separation process. Now, starting from the ammonia decomposition section, this is the catalyst we use. So you can see it's now from powder beads, and then it gets bigger. Then we use like this dome-shaped catalyst, which is with ruthenium catalyst. And these are stacked in 10 of them is stacked, and then these one pipelines is almost there are 5 pipelines. So a lot of ammonia gets in, and then once they go through this catalyst, it gets in. So once they decompose, you get unreacted ammonia. Reacted ammonia, nitrogen, and hydrogen, and then we're going to unreacted ammonia. This is called a technique called temperature swing absorption. We say a TSA. It's very simple. These columns are filled with zeolites. So once the first stream from the reactor goes through, the unreacted ammonia is absorbed on the zeolites, and then the hydrogen nitrogen mixture goes out. Once this column is full with unreacted ammonia, it moves to the second column, right? And then the absorption happens again. And then the first column, you increase the temperature and then you detach the ammonia. And then you emit it to air. So this is how you actually remove unreacted ammonia. And then if the second one gets full, then it moves to the third one and the fourth one. So once the unreacted ammonia is removed, now we have a mixture of hydrogen and nitrogen. That is separated using a technique called pressure swing absorption. Now, pressure swing absorption is basically, I don't know, anyone use GC, gas chromatography? Basically, it's the same thing, it's a big GC. So basically, it uses pressure to, so there's one column basically has absorbent, and nitrogen and hydrogen is going in. This is example of oxygen. Nitrogen absorbed in the column, and then hydrogen is separated with increasing pressure. And once this is done, you decrease the pressure and detach the nitrogen. And this is how you separate hydrogen and nitrogen. Actually, so I'm a chemical engineer, but I actually didn't know about this process before when I was a PhD student. But this is a very general way of separating nitrogen from air or separating oxygen from air. Very common way in industry to separate gas molecules. So this is the whole picture of what we have. So this is the ammonia. This is the TSA. This is the TSA. Do you think it's big? 1.4 kilogram of hydrogen per hour. So if you run this 3 hours, you can charge one car. It looks big, right? So this has to be optimized. The size has to be optimized, and there is a company right now that's doing that. Of course, this has to get smaller and smaller, like the regular fuel station that we have using gasoline. Okay, and then this is so 1.8 kilogram is this much of hydrogen, so 20 cubic meter per hour. And then a South Korean company made 300. So now it's 1 hour, 27 kilograms, that's 5 times hour. So it's now a reasonable size for a fuel station. And then this is a Korean company called One Materials, and they actually built it. This is the catalyst stable catalytic activity. It was stable for 300 days. This is the catalyst that we actually transferred our technology. So if you want to, for example, if you build a very good catalyst in lab, for example, and if you want to sell it to a company, they won't buy it unless you give them a stability for 1 year, at least 1 or 2 years. So the corporate doesn't buy that. You have to first show them the stability. So in our case, we had to run more than a year, showing that this ammonia decomposition is very stable. And then eventually the company said, okay, yeah, we're going to buy that. So this company actually we did a technology transfer for that. And then the government said that, okay, now we have to increase the size to 1,000. This is a very big size. This is almost a plant. So this is right now going on in South Korea. It's gonna be done in 2025. This is the largest ammonia decomposition plant in the world right now. The reason is everybody focused on ammonia synthesis, right? Only South Korea and Japan is focusing on ammonia decomposition. That's why we have the largest capacity in the world at this point. This is basically the same, but if you think about it, like let's say, so ammonia goes in, right? It decomposes, and then I said unreacted ammonia is absorbed, right here, and then hydrogen and nitrogen separated. But and then where did I said we just emit to air, right? But you can't emit ammonia just to air because it's also bad for the environment. So what this does, once again, let me start from here. Okay, so this temperature is 600 degrees. Okay, if you want to decompose ammonia 600, you need a 600 degree temperature. How do you get 600 degrees? How do you get heat? You burn something, right? You burn something to get heat, right? So if you want to get heat, what do you burn? You burn natural gas and coal, right? That is carbon dioxide again, right? So this is the problem again. If this gets bigger and bigger, and if this requires heat, you need to burn natural gas, which means it's not a complete CO2 free process. So what they did is they are burning unreacted ammonia a little bit, and then from here you get hydrogen, right? You burn hydrogen as well. So you burn ammonia and you burn hydrogen to get the heat for the reactor. Yeah. So, but the problem is burning hydrogen, what you get? You get water, so it's fine. But burning ammonia, what you get? You get NOx, NOx, right? So that NOx and N2O is also a greenhouse gas. So there's another problem now. But that's why this project aims to, there's a certain level where you can emit NOx emission, and that's incorporated in this project. So eventually, burning ammonia and hydrogen is the key to get a complete CO2-free process. This is not just ammonia decomposition, all kinds of reactions. If you need heat, you need to cannot burn natural gas anymore. It is for the next step. Ammonia and hydrogen. I don't know, have you tried burning ammonia, hydrogen in the lab? But hydrogen burns quickly, right? If you have a lighter, it burns quickly. Ammonia, it doesn't. You can't burn. So it's very difficult to burn ammonia. So what they do is they decompose ammonia a little bit or mix with hydrogen, and then if you ignite it, it starts to burn. So this is another very big application at this point, because if you think about it, let's say in South Korea we import ammonia, right? Like, and then we create hydrogen, and eventually we feed it to fuel cell. But what if you can just burn ammonia, right? And then just put it into a turbine, then you can generate electricity, right? Then you don't need to decompose, you don't need a fuel cell. You can use, right now, you can use just the fossil fuel based turbines, steam turbines, right? So that's another idea where you don't have to decompose, you just burn ammonia and oxidize, basically combust ammonia right away. Okay, for ammonia decomposition, Japan also have developed, but this is also a very small size, basically same thing, cracker, preturn, and everything. But this was I got it from a presentation slide from one of the Japanese university presentation, and at that point they said they're gonna make 300 to 1,000 cubic meter per hour ammonia decomposition system. But after that, everything got kind of quiet. No information was revealed. So we were wondering what are they doing, and eventually Japan moved to combustion. Like I said, burning ammonia instead of decomposing it and then using it into a fuel cell. So this is Japanese roadmap. They have a roadmap for fuel ammonia. You cannot see it, but eventually what they said is, to look at here, it says full ammonia power generation. So full ammonia combustion. So they're gonna combust ammonia and then put it into a turbine, and then just generate electricity. So they are very focused on this combustion of ammonia and combustion of hydrogen. Of course, South Korea also are trying to combust very well, but we are also trying to combust. So make cold electricity generation plant mixed with ammonia, and then natural gas is mixed with hydrogen, and then burn it because it does not generate carbon dioxide. Okay, and then there's another ammonia decomposition from Australia. They are also working on this. They use a membrane reactor. So from what I showed you so far is ammonia decomposition, and then you remove unreacted ammonia, and then you have a purification technique. right? If you use a membrane reactor, basically this membrane is coated with ruthenium catalyst. As soon as it hits, it decomposes, and then only the hydrogen goes through the membrane. So everything is can be done in one step. The purification and everything. So this is a very good way, but this membrane is very expensive, usually. Palladium membrane, and then this is very difficult to scale up. So right now, this is for a very small size applications. Okay. And then another very big application is power generation for the ship, boats, ships, large ships. They also trying to do is ammonia, make decompose ammonia and then generate, put it into a fuel cell and then move the ships using ammonia-based energy. And then those ships usually, but if you want to put it into a ship, the whole system, ammonia, decomposition, purification, removal, there's no space in the ship. So what they do is they, like I said, they just combust ammonia and then use it as a ship engine, use it for a ship engine. But as I said, ammonia doesn't get combusted well, so they decompose slightly a little bit and then they mix it with hydrogen. They just put it into an engine and then get the energy to operate the ship. So this is a very big application as well. Okay, this is a company called Ammonia Energy. This is like a startup company. This is a US-based company. Actually, so from our group, there was one senior researcher who was working with me, and then he got a PhD from MIT. So they have friends from MIT students, four friends. And then they had an idea, because they were working with us, they thought maybe, oh, it's a very good idea to start a business. Okay, so they are very young, like maybe a little bit older than the guys, but they're in a very younger stage. They started a startup company in the United States. Their corporation is in Manhattan right now. They got funding from all over the world. They've got very big right now. This is like almost the biggest company in the world right now. Using ammonia as an energy. Maybe I should have joined them, but I think they are it became very big. So what they did is basically the same thing. Do you remember where we had ammonia decomposition and then it was not wireless. There was a line, right? And then we flew a drone. They made that whole process in a drone. So if you look at this drone, this is the ammonia decomposition reactor. This is the ammonia storage tank. This is the fuel cell. So this whole thing is in the drone. Okay, so everything is in wireless. They started from drone, and then they moved to a tractor. If you look at here, this is the fuel cell, this is the ammonia tank, this is the reactor. Okay. So they did a tractor, and then they moved to this here, they moved to a semi-truck, 200 kilowatt. Again, reactor, ammonia tank, and a fuel cell. And then this is the power pack they made. Very small compared to what I showed you in 3 years ago. Right? They almost made a very, very small, almost like 1 to 20th smaller size. And then they are selling at this point right now. They also they are trying to work on the put it in a boat. And then they're trying to apply this into other applications as well. But the reason I'm showing it, this is like the biggest company at this point, and also trying to say that they are doing a lot of applications using ammonia energy. But as I said, this workload is very small, right? So this power pack is enough for this boat, but if it gets bigger and bigger, eventually you have to combust ammonia and put it into an engine. So that's another application. I think I'm almost. I have, I think, 2 or 3 more slides. Now but all of this technology to be viable, again, ammonia price has. This is the ammonia price. As I said, it spiked up to $1,000, almost $1,000 You can never produce ammonia as an auxiliary carrier in this one. This is so expensive. Eventually, everybody says it has to be around 300 to really use ammonia. Okay, this is last time. I went to a conference and someone said this. I kind of liked it, but this is what future oil will be ammonia. Right now, the oil will be changed to ammonia in 2050. And as you can see, a lot of works are going on in terms of ammonia synthesis, in terms of ammonia decomposition, in terms of ammonia combustion. A lot of works are going on. And this is and then if you look at what they're basically saying is right now the society that we are living in is based on C, it's carbon, C chemistry. And then what they're saying is that will change to N, nitrogen chemistry. So nitrogen chemistry basically get water electricity, you synthesize ammonia, you burn ammonia or you decompose ammonia to get hydrogen and then use it as an energy source to produce electricity or produce heat. Eventually for the future. Yeah, that is my end of my presentation. Thank you for your attention. Thank you very much. Okay. Thank you very much, Professor Sohn, for the presentation. So maybe I will kind of summarize about 2 or 3 sentences. One minute. So basically, from the industrial revolution, right? We get the energy from coal, then we go for the fossil fuel, and nowadays we are transferring to hydrogen. And hydrogen from this Professor Sohn patient, not only hydrogen, maybe we will move to ammonia as a hydrogen carrier or something. So as you can see, this is the technology as are developed in the global. Right now in Indonesia, we are only focusing on battery, right? But in the more developed country, hydrogen is much more greener technology as is speaking. So that's why this is quite new for the research topics, quite new also. Okay, maybe we will go through the Q&A session. Is there anyone who would like to ask Dr. Sohn, Professor Sohn about this ammonia energy, hydrogen energy? Okay, please.
My name is Hyun. I'm a student. So I'm working on Brazil as well. Actually, the thing that I want to ask about is this is all of this process production that using the spacecraft or rockets actually does they relate to this? Yeah. The hydrogen fuel cell that we use in spacecrafts or rockets, does it get all of that hydrogen from ammonia as well?
Oh, you mean the for the fuel cell in South Korea? Yeah. So, oh yes, because so the hydrogen source will mostly come from. I mean, not all of them. Of course, you cannot have only one option, right? Like because what if the ammonia price gets high? You cannot. So that in that case, we have to use liquid hydrogen, and then there's another application which is liquid organic hydrogen carriers and other methods. So, but for the fuel cell, yes, because for the fuel cell, usually Hyundai Motors is asking 99.99%. They ask in high purity hydrogen for the cars. But a lot of experts say that you can just have nitrogen in it. It will not interfere with the stability of the fuel cell. So yes, to answer your questions, most of them will come from ammonia, of course, from importing ammonia and then generate hydrogen, pure hydrogen, or a mixture of nitrogen and hydrogen to feed to the process. Yeah. Yeah, no problem.
Okay. So yes, my name is Sohn. My name is Rahman and I'm currently a second year student in chemistry. I'm going to ask you, in order to utilize ammonia as a fuel in larger scale, we have to combust it. We have to make private combust ammonia. But based on my knowledge, based on some review that I have read, it says that if we combust ammonia, it also emits some kind of greenhouse gases like M2O or MOX, like what you say. But what as we call it ammonia as a living source of energy, if we still emit greenhouse gases, and that's it.
Right. So that's a very good point. Bad, it's worse than carbon dioxide. Basically, it's way worse than carbon dioxide. And so, but of course, the emission amount is very small. But the experts is saying that it's much easier to deal with NOx because we already have NOx catalysts, right? Three-way catalysts, all kinds of catalysts. Some people say, of course, if the scale gets bigger, we never encounter that scale, right? Of course, like you say, the amount of NOx will increase. Some people say, criticizing people say, we cannot deal with that amount of NOx. Eventually, it's not a very green way to do that. But some also, on the other hand, they say, we already have to deal with NOx catalyst emissions. It's very easy to reduce to nitrogen. And so that's another way. But I personally think when I talk to people, I think it's very doable to deal with that kind of emission. And then also they're trying to, so for combustion, for combustion, it's not a matter of what kind of catalyst you use. It's about how you design the combustion, unit. If you have, where are you going to put the holes? Where are you going to start the ignition? So that, in that case, if you design it well, the NOx emission goes down a lot. So that's another field that we're actually working to reduce the NOx emission.
Is there anyone else? Yeah. Okay. Good morning, my name is Sohn, master's degree student in physics. Actually, I'm going to ask about the hydrogen storage. As according to my knowledge, people are saying that it is also a difficult task or challenging task to store hydrogen. So my question is about does the scientists or the people they got the grip on the hydrogen storage at industry level or not till now?
You mean the hydrogen? You mean in terms of hydrogen storage?
Yeah, like the people they're saying it's very difficult to make such a container to store the hydrogen. Yeah. So does they got the grip on industry level to make such a container to store the hydrogen?
Right. So of course, when we import ammonia, we need an ammonia tank. Right? The amount of ammonia that we are anticipating to import is almost 100 times higher than now. So what the government is trying to do is they are trying to convert liquid LPG tanks to ammonia tanks. So that's another solution. Then the other way, like if you produce pure hydrogen, you need to store it. Mostly, they are the companies like Linde, Air Products, they already have those. So from like the company from the United States and Europe, they already have storing liquid hydrogen from 1990s. Although the amount was very small, but they're building their increasing the scale. So in South Korea also we're developing liquid hydrogen storage. For gas hydrogen, of course, gaseous hydrogen you need a big tank, a thick tank, right? And then it's so heavy. So these are not used for large scale hydrogen storage, but mostly for transportation within very short distance. Because they're you just have to open the tank to get the hydrogen. So high pressure tanks are used for very short distance. And then, like I said, the metal hydrogen is used for submarines application where we need a very heavy liquid. So there are different applications, but I think for large hydrogen storage, we see it.
Thank you. Okay. Maybe one more question. We will take one more question. No? Okay. Again, give a big applause to Professor. Some kind of problem of decision from head of the department. Sorry, Professor. One, two, three. And we have kita akan ada foto seksi ya. Jadi enaknya gimana nih? Tadi kata Pak Asep lebih enak Profesor Sohn di tengah, kita yang foto dari sini, oke nggak?
Masing-masing. Ya, oke.
Ini saya cabut ya.
Oh iya.
Bentar. Ini cabutnya gimana?
Oh, benar-benar. Iya. Dan satu lagi, karena dari proses ini kan dari KIST ya, kebetulan dari faculty member dari KIST akan ada